November 3rd, 1944. 0930 hours. Aachen, Germany. Temperature 12 degrees Celsius. Light fog reducing visibility to 400 meters. Obersturmführer Klaus Richter, commanding a Tiger I tank of the 501st Heavy Panzer Battalion, peers through his commander's optics at what appears to be a standard American Sherman tank advancing down the rubble-strewn street. His experienced eye calculates distance, angle, ammunition type needed. 600 meters. Perfect killing range. His gunner, Unterscharführer Werner Vogel, already has the target centered in his sight. Vogel reports with practiced confidence. 76mm gun variant. Frontal armor is 51mm maximum. Our 88 will punch through like cardboard. Richter nods, allowing himself a thin smile. In 2 years of combat across Russia, North Africa, and now the Reich's western borders, he's destroyed 43 Allied tanks. Most were Shermans. The mathematics were simple and brutal. The Tiger's 88mm KWK-36 gun could penetrate a Sherman's frontal armor at 2,000 meters. The Sherman's 76mm gun might penetrate a Tiger at 300 meters under perfect conditions, with perfect ammunition and perfect shot placement. This engagement would be over before it began. Load Panzer Granit 39. Richter orders. Armor piercing with ballistic cap. The standard anti-tank round that had made the Tiger the most feared tank on any battlefield. Vogel confirms the loading with mechanical precision. Panzergranit Drehnuhn. Loaded. But something nags at Richter's combat instincts. This Sherman looks different, bulkier somehow. The turret seems more massive. The hull sits lower, heavier on its suspension. The armor plating appears thicker, with additional welded sections visible even through the fog. Wait, Richter mutters, adjusting his optics for maximum magnification. This isn't a standard Sherman. Look at the hull thickness, and those extra armor plates. Before he can finish the thought, the Sherman's 76mm gun flashes. Richter has commanded a Tiger long enough to know what's coming. The crew braces instinctively for the impact that will either ricochet harmlessly off their impenetrable frontal armor, or perhaps in the worst case, penetrate and kill them all. The American shell strikes dead center on the Tiger's frontal glacis. 100mm of face-hardened armor plate, sloped at 10 degrees, mathematically calculated to defeat any Allied anti-tank weapon in existence. The shell penetrates cleanly. Vogel screams once before the overpressure kills him instantly. Richter has exactly enough time to process the impossible. A Sherman just frontally penetrated a Tiger at 600 meters. Then the ammunition stows ignite, and the Tiger becomes a funeral pyre for its 5-man crew. 400 meters behind the burning Tiger, Staff Sergeant Clarence Smoyer, commanding the Sherman Eagle 7 of the 3rd Armored Division, lowers his binoculars. His hands are shaking. Not from fear, from the realization of what just happened. Did we just? His gunner, Corporal John Dirigi, starts to ask. We killed a Tiger, Smoyer confirms, his voice carrying a mixture of disbelief and vindication. Head on, at 600 meters. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The loader, Private James Bates, whistles low. I thought that was supposed to be impossible. Everyone said the Tiger's frontal armor was. It is impossible. Dirigi interrupts. Or it should be, unless. His voice trails off as he looks down at his Sherman's interior, at the extraordinarily thick armor plates surrounding them, at the reinforced turret casting that had seemed absurdly heavy when they first received this strange variant weeks ago. Eagle 7 wasn't a standard Sherman. It was an M4A3E2. The assault tank variant, the one American tankers had started calling the Jumbo because of its massive armor protection. And that armor, that revolutionary, supposedly impossible armor, had just changed everything about how tank warfare would be understood. What Klaus Richter didn't know, dying in his burning Tiger on that foggy German street, was that the armor that killed him represented a metallurgical breakthrough that had been declared theoretically impossible by German, British, and even American experts. that a single metallurgist working in near-total secrecy had solved a problem that had defeated every other engineer who attempted it, that the forbidden armor plate protecting the jumbo shouldn't exist according to every accepted principle of metallurgical science in 1944, and that this impossible armor was about to make the already formidable Tiger tank the terror of Allied tankers for 2 years, suddenly vulnerable to what had been considered the weakest tank in the Allied arsenal. January 1944. Fisher Tank Arsenal, Grand Blanc, Michigan. Temperature, -8 degrees Celsius. Constant snow. Dr. Edgar Zanotti, senior metallurgist for General Motors Tank Armor Division, stared at the metallurgical test results spread across his desk with the expression of a man confronting physical impossibility. The numbers didn't merely indicate failure. They indicated that what the Army Ordnance Department wanted, what they desperately needed, violated fundamental principles of materials science. You couldn't have both. That was the absolute, inviolable law of armor metallurgy that every expert in America, Britain, and Germany accepted without question. High hardness for maximum penetration resistance, or high toughness for resistance to cracking and shattering. Choose one. You couldn't have both. The technical specifications from the Ordnance Department demanded the impossible. They wanted armor plate for a new Sherman variant, an assault tank designed to lead breakthrough operations against fortified German positions. This tank needed to survive direct hits from German 88mm guns. The current Sherman's frontal armor, 51mm at 47 degrees, couldn't stop an 88 beyond 800 meters. Even the improved M4A3 with 64mm of frontal armor only pushed that survival envelope to maybe 500 meters under optimal conditions. The new assault Sherman would need at minimum 100mm of frontal armor, preferably more. And that armor needed to be rolled homogeneous armor RHA, the standard type that could be produced in quantity using existing mill facilities. No exotic alloys. No special heat treatments that required specialized equipment. Just better armor made from the same basic steel they were already using. It's mathematically impossible, stated Dr. Robert Franklin, Chief Materials Engineer for the Fisher Arsenal, during the project meeting on January 15th. You achieve hardness through high carbon content and specific heat treatment, but high carbon content makes steel brittle. You achieve toughness through lower carbon content and different heat treatment, but lower carbon reduces hardness. These are mutually exclusive metallurgical states. Zanotti knew Franklin was right. Every metallurgy textbook, every materials science paper, every practical engineering manual confirmed it. Armor steel existed on a spectrum. At one end, face-hardened armor, extremely hard surface layer over a tough backing plate, maximum penetration resistance, but prone to catastrophic cracking if the surface layer failed. At the other end, homogeneous armor, uniform, hardness and toughness throughout, less penetration resistance than face-hardened, but wouldn't shatter under repeated impacts. The Germans had mastered face-hardened armor. Their tanks used it exclusively. The Tiger's frontal plate was face-hardened to phenomenal hardness levels, making it nearly impervious to frontal attack. But German tankers reported disturbing incidents where their face-hardened armor cracked completely through after multiple hits, even hits that didn't penetrate. The entire armor plate would fracture like glass, leaving the tank defenseless. The Americans had chosen homogeneous armor for the Sherman, easier to manufacture, more consistent quality across production. Better performance against the most common threats American tanks faced, German 75mm and 88mm guns. But homogeneous armor had a fundamental limitation. Beyond a certain thickness, it became so heavy that the Sherman's engine and suspension couldn't support it. And even at maximum practical thickness, it couldn't reliably stop a Tiger's 88mm gun. What if, Zanotti said slowly, thinking through the metallurgy as he spoke, we're approaching this wrong? What if the limitation isn't in the steel chemistry itself, but in how we're heat treating it? Franklin shook his head. Edgar, we've tried every heat treatment protocol. Quenching rates, tempering temperatures, cooling curves. We've mapped the entire heat treatment space for these steel compositions. There's no combination that gives you both high hardness and high toughness. The metallurgy doesn't support it. Every documented combination, Zanotti corrected. What about combinations outside the standard protocols? What if we're constrained by conventional thinking about what's possible? The room fell silent. What Zanotti was suggesting bordered on heresy in the conservative world of military metallurgy. Heat treatment protocols existed for specific reasons, developed through decades of industrial experience and scientific study. Deviating from established procedures risked producing defective armor that would fail catastrophically in combat, killing American tankers who trusted their vehicles to protect them. You want to conduct unauthorized experimental heat treatments, Franklin said carefully, on armor plate intended for combat vehicles, armor that soldiers will depend on with their lives. I want to find out if there's a combination we haven't tried. Zanotti replied, because if we can't find it, American tankers are going to keep dying in Shermans that can't survive Tiger hits, and this whole assault tank program becomes pointless. February 19, 1944. Fisher Tank Arsenal Metallurgical Testing Facility. Test number 1. Zanotti's first experimental heat treatment protocol used higher quenching temperatures than standard specifications allowed. The theory was sound. Higher temperatures during quenching would create different crystalline structures in the steel, potentially achieving hardness levels beyond what normal protocols produced. The test plate measured 10 mm thick, small enough to process quickly, large enough to provide meaningful data. The steel composition was standard 0.30 carbon content, 0.85 manganese, 0.28 silicon, with trace elements of chromium and molybdenum for hardenability, identical to steel used in current Sherman armor. Only the heat treatment differed. Zanotti supervised the heating personally, watching the plate reach a critical temperature 850 degrees Celsius, glowing cherry red in the furnace. At precisely the right moment, he nodded to the technician, who plunged the glowing plate into the quenching oil. The violent thermal shock as 1100-degree steel met room temperature oil produced explosive boiling, the oil flashing to vapor in a roiling cloud. Standard procedure. The plate emerged black and steaming, ready for tempering to relieve internal stresses. The impact test came 3 days later, after the plate had been tempered and allowed to cool completely. A 40 mm armor-piercing projectile fired from a test gun at 500 meters. The expected result for plate this thickness at this hardness level would be complete penetration with moderate deformation. The actual result was catastrophic failure. The projectile struck dead center. The plate shattered into 7 pieces. The fragments flew across the testing range like shrapnel. One piece embedded itself in the observation bunker's reinforced wall. Jesus Christ, muttered the test range supervisor, examining the impact point. I've never seen homogeneous armor fail like that. It broke like face-hardened armor after the surface layer fractures. Zanotti examined the fracture surfaces with a magnifying glass. The crystal structure showed massive grain growth. The individual crystalline regions in the steel had grown too large during the high-temperature treatment. Large grains meant brittle behavior, exactly what they were trying to avoid. Test number 1. Complete failure. Test number 2. Zanotti reversed his approach. Lower quenching temperature, but extended time at temperature to allow different diffusion processes. Maybe slower, more controlled heating would produce the fine-grained structure they needed while still achieving adequate hardness. The second test plate cracked during quenching itself, splitting completely in half before it even reached the tempering stage. The thermal stresses from the quench were too great for the internal crystal structure. Test number 2. Complete failure before testing even began. Through March and into April, Zanotti conducted 17 different experimental heat treatments. Every single one failed. Some produced armor too brittle, shattering on impact. Some produced armor too soft, allowing complete penetration by projectiles that standard armor would have stopped. 3 plates developed internal cracks during tempering that weren't detected until impact testing caused catastrophic failure. 1 plate developed surface cracks so severe it was rejected before testing. Edgar, Franklin said during their April 28th meeting, you've run through 17 different protocols. Everyone failed. Some failed dangerously. This is exactly why we have standard heat treatment specifications, because deviating from them produces unpredictable, unreliable results. Everyone failed differently, Zanotti countered, which means we're learning something from each failure. Test 6 achieved good hardness but poor toughness, too much carbon in the martensite. Test 9 achieved good toughness but inadequate hardness, insufficient carbon in solution. Test 12 came closest, good hardness, decent toughness, but failed after 3 impacts instead of 1. We're narrowing down the correct parameters. Or, you're proving that what you're attempting is fundamentally impossible, Franklin replied. The Ordnance Department is asking for specifications in 2 weeks. We need to tell them whether this assault tank program is feasible. Can we produce armor that will stop a Tiger's 88mm gun? Yes or no? Zanotti looked at his test results, 17 failures documented in meticulous detail. By every reasonable metallurgical standard, Franklin was right. The evidence overwhelmingly indicated that what they were attempting couldn't be done. Give me 1 more week, Zanotti said. 7 days. If I can't produce a viable result by then, I'll recommend we tell Ordnance the assault tank concept isn't feasible with current metallurgical technology. May 4th, 1944, 03:15 hours. Zanotti had been in the metallurgical lab for 36 hours straight, surviving on coffee and determination. The insight had come at 0200 hours, while reviewing photomicrographs of crystal structures from failed tests. He'd been looking at the problem wrong. Everyone had been looking at it wrong. The standard approach to armor steel heat treatment involved austenitizing heating the steel to high temperature to convert it to austenite crystal structure, then quenching rapidly to convert the austenite to martensite, the hard crystalline form that provided penetration resistance, then tempering to relieve stresses and improve toughness. But what if that sequence was fundamentally flawed for thick armor plate? What if the cooling rate during quenching couldn't be uniform through thick sections, creating different crystal structures at different depths? The surface would cool first, converting to martensite while the core remained austenite. Then the core would cool more slowly, potentially converting to different structures, bainite, pearlite, softer than martensite but tougher. Standard protocols tried to prevent this differential cooling, attempting to achieve uniform martensite throughout the plate thickness. But what if they were fighting against metallurgical reality? What if the solution was to deliberately control the differential cooling, engineering specific crystal structures at specific depths? A hard martensitic surface for penetration resistance, a tough bainitic core for crack resistance, and a carefully controlled transition zone between them to prevent delamination. It would technically be a form of face hardening, but unlike German face-hardened armor, which achieved its hard surface through chemical carburization or extremely violent quenching that created dangerous internal stresses, this would be gentler, controlled. The hard layer would be thinner, the transition more gradual, the internal stress levels manageable. The 19th test plate went into the furnace at 0400 hours. Zanotti had calculated everything precisely, heating to 820 degrees Celsius, slightly below the standard temperature, holding for exactly 45 minutes to achieve complete austenitization. Then the critical step A, modified quench. Not the violent, full immersion that created catastrophic thermal shock. Instead, spray quenching. Multiple small jets of oil striking the surface, cooling it rapidly while the core cooled more gradually. The cooling rate differential was carefully calculated to produce martensite to a depth of 15 millimeters, with bainite forming below that depth. The plate emerged from the quench intact, no visible cracks, no warping, tempering at 400 degrees Celsius for 2 hours to relieve stresses, then a second tempering at 350 degrees to further refine the structure, cooling to room temperature over 24 hours. May 6th. The test plate went to the firing range. Zanotti watched through reinforced glass as the test crew loaded a 40mm AP projectile into the test gun. 500 meters range. The gun fired. The projectile struck the plate dead center, producing a distinctive metallic clang. The plate rang like a bell, a good sign, indicating energy absorption rather than brittle fracture. When the smoke cleared, Zanotti walked to the target with his heart hammering. The projectile had failed to penetrate. The impact crater measured 18 millimeters deep, deeper than standard homogeneous armor would show, but hadn't broken through the plate's 40-millimeter thickness. More importantly, the plate showed no cracking around the impact point, no deformation beyond the immediate crater. The crystal structure had absorbed the impact energy without catastrophic failure. "Load the 88-millimeter equivalent," Zanotti ordered. The test crew looked at him in surprise. Standard protocol was to test progressively, slowly increasing projectile size and impact energy. Jumping straight to 88mm equivalent 75mm American gun firing, high-velocity AP, risked destroying the test plate before they could gather complete data. If this armor can't stop an 88mm hit, it's useless for the assault tank program, Zanotti explained. Let's find out now. The 75mm gun fired, heavier recoil, louder report, the projectile traveling at 810 meters per second, equivalent to a German 88mm Panzergranate, 39 at 500 meters, struck with devastating force. The plate held. Partial penetration. The projectile created a crater 42 millimeters deep in the 40mm test plate, technically complete penetration by metallurgical definitions, but the projectile itself fragmented, its energy dissipated by the layered crystal structure. No spalling on the back face, no cracks radiating from the impact. The plate had failed to completely stop the penetration, but it had defeated the projectile's ability to cause damage. "We need a thicker plate," Zanotti said quietly. "If 40 millimeters can almost stop an 88mm equivalent, 100 millimeters should stop it completely, with safety margin to spare." If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. May 15th, 1944. Army Ordnance Department, Aberdeen Proving Ground, Maryland. The demonstration for Ordnance Department officials used 100mm test plates produced using Zanotti's modified heat treatment protocol. Colonel James Hartley, the same officer who had championed HVAP ammunition development, watched with barely concealed skepticism as test crews prepared the firing range. "Dr. Zanotti," Hartley said carefully, "your report claims these plates will stop an 88mm Panzergranate 39 at 500 meters. That's equivalent to stopping the German Tiger's main gun. Standard homogeneous armor at 100mm thickness cannot achieve this. Are you certain of your results?" "The metallurgy is sound," Zanotti replied. Crystal structure creates a damage arrest mechanism that standard homogeneous armor lacks. When a penetrator strikes, the hard martensitic surface resists initial penetration. If penetration occurs, the tough bainitic core prevents crack propagation. The projectile must defeat each layer separately, dissipating its energy progressively. "That sounds like face-hardened armor," Hartley observed. Face-hardened armor shatters catastrophically if the surface layer fails. We've seen Tiger tanks with their frontal armor cracked completely after multiple hits. This isn't face-hardened armor as the Germans use it, Zanotti explained. The transition between layers is gradual, not abrupt. The hard layer is thinner, only 15 millimeters versus 30 plus on German armor. And the core is bainite, not soft ferrite. It maintains significant hardness while providing the toughness we need. The test began. 100mm plate mounted vertically. Distance 500 meters. Projectile 75mm M72 AP, fired from an M3 gun, equivalent to German 88mm Panzergranate 39 in penetration capability. The gun fired. The projectile struck. The plate rang with the distinctive clear tone that indicated successful energy absorption. Inspection revealed a crater 38 millimeters deep, no penetration, no cracking, no spalling on the back face. The plate had completely defeated the projectile. Colonel Hartley walked to the plate, running his hand over the impact crater. "Fire again," he ordered. "Same spot." The second shot struck within 5 centimeters of the first impact. The plate held. Crater 41 millimeters deep now, the impact craters overlapping slightly. Still no penetration, No structural failure. Again, Hartley ordered. 5 shots total, all within a 15-centimeter circle on the same plate. The plate absorbed every impact. Maximum crater depth reached 44 millimeters after the 5th shot, but the plate's structural integrity remained intact. No penetrator achieved penetration. How much does this armor weigh compared to a standard plate? Hartley asked. Identical weight, Zanotti replied. Same steel composition, same thickness. Only the crystal structure differs. We're not adding mass, we're optimizing the metallurgy. Production feasibility. Any steel mill that can roll current Sherman armor can roll this, Zanotti confirmed. The heat treatment is more complex, but we've developed procedures that any properly equipped facility can implement. We estimate no significant impact on production rates once mills train their personnel on the modified protocols. Hartley was quiet for a long moment, staring at the test plate with its 5 impact craters, proof that American metallurgy had achieved something German engineers had declared impossible. Dr. Zanotti, he finally said, if you can deliver this armor in production quantities by August, I'll authorize the assault tank program, 100 vehicles to start. If they perform as your tests indicate, we'll expand production immediately. The assault tank program, what would become the M4A3E2, received immediate priority authorization, but the armor development that made it possible remained classified at the highest levels. German intelligence had informants throughout American industry. If they learned that American metallurgists had developed armor that could resist Tiger guns, they might develop countermeasures, higher velocity guns, heavier projectiles, different attack angles. The armor's existence would be revealed only through combat results, and those results would shock every German tanker who encountered the new American assault tanks. August 7, 1944. Fisher Tank Arsenal, Grand Blanc, Michigan. The first production M4A3E2 assault tanks rolled off the assembly line with Zanotti's revolutionary armor plate welded into their hulls. To the casual observer, they looked like standard Shermans. Closer inspection revealed the differences. The frontal hull armor measured 102 millimeters thick, double the standard Sherman's 51 millimeters. The turret front used 152 millimeters of cast armor, also using Zanotti's modified metallurgical process, adapted for casting rather than rolling. The gun mantlet added another 114 millimeters. Total frontal protection in the critical areas exceeded 250 millimeters equivalent. The additional armor added 7 tons to the Sherman's weight. Engineers compensated by using the horizontal volute spring suspension from the later model M4A3, which could handle the extra load. The result was a tank that moved slightly slower than standard Sherman's top speed, 22 miles per hour versus 30, but could absorb punishment that would destroy any other Allied tank. Production target was 254 vehicles to be completed by October 1st. Each tank cost approximately $7,000 more than a standard Sherman, mostly due to the specialized heat treatment requirements for the armor. But that cost seemed trivial compared to the tactical advantage they would provide. September 12, 1944. The first jumbos arrived in France, assigned to the 3rd Armored Division. No special fanfare, no announcement of their capabilities. Battalion commanders received sealed orders explaining the assault tank's armor protection and tactical employment guidelines. Crews received one critical instruction. When engaging German heavy tanks, Tigers or Panthers close to within 500 meters before firing, the jumbo's armor could survive the approach. Standard Shermans could not. But even with the extraordinary armor protection, the jumbo still mounted the same 76mm M1A2 gun as other Sherman variants. Against Tiger frontal armor, at normal engagement ranges, that gun remained marginally effective at best. Staff Sergeant Clarence Smoyer received his Jumbo Eagle 7 on September 18th. His first reaction was disbelief at the armor thickness. "Sir," he asked Lieutenant William McVeigh, his platoon leader, "are we sure this tank can even move with all this armor?" "It moves," McVeigh confirmed. "Just not as fast." "But Sergeant, that armor will stop anything the Germans can shoot at you. Tiger, Panther, 88mm anti-tank gun. None of it will penetrate your frontal arc. You're going to be the tip of the spear for every assault we conduct. The other Shermans will follow behind you because you can take the hits they can't. Smoyer climbed into Eagle 7's turret, examining the interior. The additional armor created a more cramped fighting space, but not unbearably so. The gun controls felt familiar, identical to the standard Sherman. The optics, the communications equipment, the ammunition stowage, all standard. Only the walls were different. Thicker, heavier, theoretically impervious. "What if the intelligence is wrong?" asked Corporal John DeRiggi, Smoyer's gunner. "What if a Tiger can penetrate this armor anyway? What if we're being sent into situations that would normally require air support or artillery, and we get killed because someone miscalculated how good this armor really is? Then we die the same way we'd die in a regular Sherman," Smoyer replied flatly. "But the Ordnance Department doesn't build 200 tanks with special armor unless they're pretty damn sure it works. So we're going to trust it. Because if we don't trust it, we'll hesitate when we need to advance, and hesitation gets people killed faster than enemy fire." Eagle 7 saw its first combat 3 days later, September 21st, village of Morsbach, Germany. American forces advancing into German territory encountered prepared defensive positions anchored by a Stug 3 assault gun 75mm gun, low profile, dug into a concealed position covering the main road. Standard Sherman doctrine would be to call for artillery or air support, suppress the position, then advance. But Eagle 7 had different orders. Smoyer drove directly down the main road at the Stug position. Every instinct screamed at him to find cover, to stop presenting such an obvious target. But the tactical doctrine for the Jumbo specifically required this advance directly toward enemy anti-tank weapons, drawing their fire, allowing other tanks to maneuver into flanking positions while the enemy focused on the seemingly suicidal assault tank. The Stug fired at 300 meters. The 75mm Panzergranate struck Eagle 7's frontal glacis with tremendous force. The impact threw Smoyer against his seat restraints, the interior filled with the deafening clang of steel on steel. Every crew member flinched, waiting for penetration, fire, death. Nothing happened. The round ricocheted, leaving a bright scar on the armor but failing to penetrate. "Holy shit!" breathed Private James Bates. The loader. "It actually works." "Gunner! Stug! 300 meters!" Smoyer ordered, his voice steady despite his racing heartbeat. "Identified," DeRiggi confirmed, already traversing the turret. "Fire!" The 76mm gun bucked. At 300 meters, even the Sherman's gun could penetrate a Stug's frontal armor. The German assault gun erupted in flames as the American armor-piercing round tore through its fighting compartment. Eagle 7's crew sat in stunned silence for a moment, processing what had just occurred. They'd been hit by a German anti-tank gun at close range. They'd survived without injury. The armor worked exactly as promised. "Well," Smoyer finally said, "I guess we're going to be doing a lot more of these frontal assaults." October 9th, 1944. Aachen, Germany. The first major German city to fall to Allied forces. Urban. Combat the worst possible environment for tanks. Buildings provided countless hiding positions for German Panzerfaust teams. Streets channeled movement, preventing maneuver. Every corner potentially concealed an anti-tank gun, or heavy tank. The 3rd Armoured Division's assault on Aachen relied heavily on their jumbos. Standard Shermans provided fire support from covered positions. The jumbos advanced into the kill zones, absorbing hits, identifying enemy positions, allowing infantry and other tanks to maneuver safely. Eagle 7 took 11 hits during the Aachen fighting, 2 from Panzerfaust hollow charge weapons, terrifying explosions that did no internal damage, 4 from 75mm anti-tank guns, all ricochets or partial penetrations that failed to breach the fighting compartment, 3 from an unidentified high-velocity gun, possibly an 88mm, that left deep craters in the armor but didn't penetrate, 2 from machine gun fire that did nothing but scratch the paint. "We're basically invincible from the front," DeRiggi observed, after examining the battle damage. "Every hit that would have killed a regular Sherman just bounced off or stopped in the armor. This is insane. "We're not invincible," Smoyer corrected. "Side armor is still 51 millimeters, rear armor 38. Any decent anti-tank weapon will go right through if they hit us from an angle. And a Tiger can still penetrate our turret sides at close range. We're only invincible if we keep our front toward the enemy." But the psychological impact of the jumbo's armor protection was profound. Crews gained confidence that translated directly into tactical aggressiveness. They advanced into situations that would have been suicidal in standard Shermans. They drew enemy fire deliberately, tanking hits that would have destroyed other vehicles, creating opportunities for infantry and supporting tanks. German forces began reporting encounters with what they called Sherman Tigers, American tanks with armor protection comparable to German heavy tanks. Initial reports were dismissed as panic or exaggeration. Every German tanker and anti-tank gunner knew that Shermans had thin armor vulnerable to any decent German weapon. Claims that some Shermans were now bouncing 88mm hits seemed like fantasy, but the reports continued, and they came from experienced, reliable observers. Panzer crews with dozens of Sherman kills to their credit, suddenly reporting that their normally effective weapons were failing against certain Sherman variants that looked slightly bulkier than standard. November 3, 1944. The engagement that opened this story. Obersturmführer Klaus Richter's Tiger versus Staff Sergeant Clarence Smoyer's Jumbo, 600 meters. Urban environment limiting maneuver. Richter had every tactical advantage: heavier gun, better optics, more combat experience, superior position. He should have destroyed Eagle 7 with his first shot. Instead, his 88mm Panzergranate struck 102mm of Zanotti's revolutionary armor. The projectile's hardened steel penetrator encountered first the martensitic surface layer, 15mm of extremely hard crystalline structure that resisted initial penetration, abrading the penetrator's tip, creating heat and friction that began degrading its penetration capability. Then the bayonetic core, 87mm of tough crystalline structure that absorbed the penetrator's kinetic energy progressively, creating microcracks that dissipated impact forces without allowing catastrophic crack propagation. The penetrator fragmented approximately 60mm into the plate, its remaining energy insufficient to complete penetration. The armor held. The Tiger's supposedly unstoppable 88mm gun, the weapon that had dominated Allied armor for 2 years, had been defeated by American Metallurgy. And Smoyer's return shot, fired from Eagle 7's 76mm gun, loaded with HVAP ammunition, found the Tiger's frontal glacis at an angle where even the German tank's formidable armor couldn't prevent penetration. The Tiger burned. Richter died. And the tactical calculus of armored warfare shifted fundamentally. If Shermans could now survive Tiger hits and kill Tigers frontally, the German heavy tank's overwhelming advantage had been neutralized. Not eliminated, a Tiger still had a better gun, better optics, better trained crew in most cases, but no longer the absolute guarantee of survival in frontal engagement. The invincibility that German tankers had relied upon was gone. German tank commanders began receiving urgent intelligence bulletins in mid-November. Warning: American forces employing heavily armored Sherman variant. Frontal armor estimated 100mm minimum. Standard Panzergranate 39 may fail to penetrate frontally. Recommend flank shots or use of Panzergranate 40 tungsten core ammunition when available. But Panzergranate 40 was in desperately short supply. Germany's tungsten sources had been cut off by Allied advances. The special tungsten core ammunition that could defeat heavy armor was being reserved for specific critical situations. Most German tank crews had to rely on standard steel core Panzergranate 39, which couldn't reliably penetrate the Jumbo's frontal armor. December 16, 1944. The Battle of the Bulge began Germany's massive winter offensive through the Ardennes forest, intended to split Allied forces and recapture Antwerp. The operation committed Germany's last strategic reserves, including newly formed heavy tank battalions equipped with Tiger II, King Tigers, mounting longer 88mm guns with even greater penetration capability than the original Tiger. Against standard Shermans, the King Tiger was devastating. Its frontal armor 150mm at 50 degrees was essentially immune to Sherman guns at any practical range. Its gun could penetrate any Allied tank at ranges exceeding 2,000 meters. Tactically, it represented German armor superiority at its absolute peak. But scattered throughout the American tank battalions caught in the German offensive were the jumbos. Not many total production hadn't exceeded 254 vehicles, but enough to make a difference in critical engagements. Staff Sergeant Lafayette Green-Poole, commanding a jumbo from the 3rd Armored Division's Task Force X, encountered a King Tiger near the town of Stavelot on December 19th. The engagement occurred at 700 meters point-blank range for a King Tiger's gun. The German tank fired first. The 88mm projectile from the King Tiger's improved gun struck Poole's jumbo dead center on the frontal glacis. 102mm of Zanotti's armor absorbed the impact. Partial penetration, the crater reached 88mm deep, but the projectile fragmented before complete penetration. No damage to the crew or internal systems. Poole's gunner fired immediately, aiming not for the King Tiger's frontal armor futile even with HVAP ammunition, but for the gun mantlet, the thick casting surrounding the main gun. At 700 meters with HVAP, the Sherman's 76mm gun achieved penetration through the mantlet's edge, a weak point in the King Tiger's otherwise impregnable frontal protection. The German tank's ammunition detonated. The King Tiger, the most powerful production tank of World War II, killed by a Sherman that shouldn't have survived the first shot, but survived because one metallurgist had refused to accept that certain metallurgical properties were mutually exclusive, had insisted there must be a combination that produced both high hardness and high toughness, had conducted 19 different experimental heat treatments until he found it. The jumbo's combat record through the remainder of the war was remarkable. Of the 254 produced, approximately 40 were lost to enemy action, but analysis of the destroyed vehicles revealed something extraordinary. Not one jumbo was penetrated through its frontal armor by German weapons. Every vehicle lost was hit from the side or rear areas with standard Sherman armor thickness, or was destroyed by internal fire after ammunition, stowage was hit, or was disabled by track damage and subsequently abandoned. The frontal armor, Zanotti's forbidden armor that combined high hardness and high toughness, remained undefeated throughout the war. German metallurgists, examining captured jumbos after the war, were baffled by the armor's properties. Hardness testing showed surface hardness, equivalent to German face-hardened armor, but core samples showed toughness levels typical of homogeneous armor. The combination seemed impossible. How did they achieve this? Asked Dr. Heinrich Müller, a metallurgist who had worked on Tiger armor development, while examining a captured jumbo at a British intelligence facility in July 1945. The heat treatment required to produce this hardness should create brittleness in the core, but the core is tough, ductile. This violates basic metallurgical principles. British metallurgist Dr. William Cross, who had been briefed on Zanotti's work, smiled slightly. It doesn't violate principles, it exploits principles that your specifications didn't consider. The differential cooling rate through thick sections, the controlled formation of different crystal structures at different depths. Your face-hardened armor tried to create an extremely hard surface through chemical means carburization. This achieves similar hardness through purely thermal treatment, with a much more gradual transition to the tough core. Less stress concentration. Better crack resistance. Ingenious, Müller admitted. We focused so intently on maximizing surface hardness that we never considered there might be better ways to achieve the same result. Our metallurgical doctrine became dogma. We stopped questioning whether alternatives might exist. It was a fitting epitaph for German armor development. Superior at the war's start through careful engineering and established doctrine, but ultimately surpassed because American metallurgists were willing to question established doctrine, to experiment with forbidden combinations, to pursue solutions that conventional wisdom said were impossible. Dr. Edgar Zanotti received the Medal for Merit in October 1945 for his work on armor development. The citation was classified. The armor's metallurgical details remained secret throughout the Cold War, only being declassified in the 1980s. Zanotti never sought publicity for his achievement. He returned to General Motors' research division, continuing metallurgical research on automotive applications, living quietly until his death in 1987, at age 84. Most historical accounts of the Sherman tank mention the Jumbo as a footnote, a limited production variant with heavy armor, interesting but not particularly significant to the war's outcome. They miss the deeper story. The Jumbo represented a fundamental breakthrough in metallurgical science, achieving properties that experts had declared theoretically impossible. It demonstrated that American industrial innovation could match and exceed German technical sophistication when given proper support and freedom to experiment. And it proved that conventional wisdom in metallurgy, in engineering, in any field, should be constantly questioned and tested. The lessons from Zanotti's work extended far beyond World War II armor development. His differential heat treatment approach influenced post-war armor steel development, leading to modern armor that combines different material properties at different depths. His willingness to challenge accepted metallurgical doctrine influenced how materials scientists approached problems, less reliance on established procedures, more willingness to explore unconventional solutions. His documentation of 19 different failed heat treatment experiments became a teaching tool, demonstrating that failure in research isn't defeat, but rather the process of eliminating incorrect approaches to find correct ones. Klaus Richter, dying in his burning Tiger on that foggy Aachen street in November 1944, never knew what killed him. He couldn't have known that the Sherman he faced had armor developed through a metallurgical breakthrough his own country's experts would have dismissed as impossible. Couldn't have known that one American metallurgist's refusal to accept limitations had made his supposedly invincible tank suddenly vulnerable. Couldn't have known that the future of armor development had shifted fundamentally, that the careful German approach of incremental improvement based on established doctrine had been surpassed by the American approach of questioning everything and experimenting aggressively. The Tiger tank remained formidable until the war's end, but it was no longer invincible, and that psychological shift, the knowledge that German heavy tanks could be defeated by upgraded Allied tanks in frontal combat, changed how both sides approached armored warfare. American tankers gained confidence, German tankers lost the absolute certainty of superiority. And in armored combat, where psychology and confidence directly influenced tactical decision-making, that shift mattered as much as the armor's actual technical capabilities. The M4A3E2 Jumbo served with distinction until the war's end in May 1945. Some vehicles continued in service with the Army through the Korean War, proving that Zanotti's armor remained effective even against more modern anti-tank weapons. The last Jumbos were retired from active service in 1957, their armor still undefeated after more than a decade of potential combat exposure. Today, approximately 10 Jumbos survive in museums and private collections. Their armor still bears the scars of German anti-tank weapons' deep craters that failed to penetrate, testimony to one metallurgist's achievement. Visitors can run their hands over those impact craters, feeling the depth of the penetration attempts, understanding viscerally how close those projectiles came to killing the crews inside, and understanding that the difference between penetration and protection, between life and death for those tankers, was measured in millimeters of carefully engineered crystalline structure. The story of the Jumbo is ultimately a story about the power of questioning assumptions. Every metallurgist Zanotti consulted told him that what he was attempting was impossible. Every textbook said you couldn't have both high hardness and high toughness. Every established procedure supported that conclusion. But Zanotti asked the critical question, what if we're wrong? What if there's a combination we haven't tried? What if the limitation is in our thinking, not in the material's fundamental properties? That willingness to question, to experiment, to accept failure as part of the process of discovery led directly to an armor breakthrough that saved lives and changed history. The lesson extends far beyond metallurgy or military history. In any field, established wisdom should be tested, rather than blindly accepted. Impossible is often simply a label applied to things no one has succeeded at yet, and sometimes the most important innovations come not from doing what experts say is possible, but from attempting what experts say is impossible and discovering they were wrong. The metallurgist who made Jumbos immune to Tiger guns never achieved widespread fame. His name doesn't appear in most World War II histories. but every American tanker who survived a German anti-tank hit that should have killed them, who watched their jumbo absorb punishment that would have destroyed any other Allied tank, owed their life to Edgar Zanotti's stubborn refusal to accept that certain metallurgical combinations were forbidden. That's the ultimate measure of innovation's value, not the scientific papers published or the awards received, but the lives saved because someone questioned whether the impossible might actually be possible after all. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.